Okay, let's get started. Today's seminar. Today's seminar speaker is Dr. Felix Kling, and he will talk about looking forward to new physics with FASER. So please start.
Okay, thank you. Yeah, I was originally supposed to give the same seminar in the end of February, but unfortunately, the Corona crisis started right the weekend before I was supposed to give the seminar. So now it will be 2 months delay, half a year delayed, but I'm still happy to talk to you and introduce you to our recent work on phasor and forward physics in general. So let me start with a general introduction. As you know, most LHC experiments focus on the central region, and this is very motivated by the kind of physics we are typically interested in. For example, searches for the Higgs boson or searches for supersymmetry. This kind of new physics is typically associated with heavy particles that are produced, or that whose decay products have large transverse momentum and are typically decaying isotropically. So you want to build a detector that covers as much solid angle as possible around the interaction point in the center and look for the particles that are produced in the transverse plane. And the typical rates for those searches that we have in mind is something in the femtobarn to picobarn range. So for example, the Higgs boson, we expect to produce 10 to the 7 Higgs bosons during the first runs of the LHC. However, if you want to look for a different kind of physics, let's say light physics, weakly coupled physics, this paradigm of looking in the central region might be completely misguided. If new physics would be light, it could be produced in the decay of standard model hadrons like pions or kaons or d-mesons. And those particles, they're mainly produced in the forward direction, not in the transverse direction, in the central region. At the same time, those very light and weakly interacting particles are also, well, weakly interacting. So they're extremely rare that we might produce them. So we need extremely large standard model rates to see them in the first place. And this motivates to look at a different region of phase space, the forward region. So what typically goes down along the beamline, where we currently do not have any detectors because, well, there's a beamline and it's a beam, and you don't want to put a detector right into the beam pipe. In this region, there are enormous event rates. So now we talk not about femtobarn or picobarn, but about millibarn and barn. So that means we would produce order of 10 to the 17 pions during the same time. So this is 10 orders of magnitude more than we produce Higgs bosons. And these particles can be incredibly energetic since they form through the hadronization of the beam remnants. Particles produced in the forward direction can have order 1 fraction of the proton beam energy, so TeV energy. And those particles are also incredibly collimated. They're typically produced at low transverse momentum, so the 2 protons just slightly collide, break apart, and form pions and kaons, which then form a very collimated beam with an opening angle of order milliradian. Of course, we can't place a reasonable sized detector very close to the beam line near the interaction point. This would block the proton beam, but also be subject to very large amount of radiations. However, if we are looking for very weakly interacting particles that do not interact much with matter, we don't have to build it close to the detector or close to the interaction point. We could build it more far away. So here is a more comic version of how the LHC looks. You have the Atlas interaction point, you have an LHC tunnel, it's straight for a while, and until the beam is cleaned and all the produced particles are filtered out, and then the LHC is roughly a circle and curves away. So you could imagine putting an experiment here that searches for light weakly interacting particles that are produced in the forward direction. This has the additional advantage that you can use the LHC infrastructure that cleans the beam, as well as 100 meters of rock, as shielding for such an experiment to create an environment that has very low rates and very low background levels. And even at a location a couple hundred meters away from the Atlas interaction point, you would still have a beam that's incredibly collimated. So you wouldn't need a big experiment, which motivates our proposal for a small, fast to build, cheap, inexpensive detector to be placed 500 meters down the Atlas interaction point, which we called FASER, or the forward searching experiment at the LHC. And this has applications for both searches for new physics, long particle searches, as well as the one weakly interacting light particle we know in the standard model, the neutrino. Just to give you an idea, we would look for a long-lived particle that enters a detector, decays into, let's say, a pair of electrons, which then are split apart by a magnet, goes through a spectrometer, so through a tracking system, and into a calorimeter so that we can measure the momentum and the energy of the particle. There's some shielding and in vitro stations in front so that we can identify such new physics signature. For neutrinos, situation is different. Neutrinos interact with material, so we would put a detector there that is very dense to increase the number of neutrino interaction. In our case, a nuclear emulsion detector. And we would look for appearing vortices where a neutrino comes in, interacts, produces a jet of charged particles, which we could then identify and look for. Okay, so this is a quick 5-minute summary of what FASER is doing. I will now go into more detail on where the experiment will be, how it will look, go through examples of for long-lived particle searches, as well as applications for neutrino physics. If you have questions, please interrupt me at any time. Okay, let's start with the FASER experiment. So when we had the idea, the first question we had to ask ourselves is, where could we put such an experiment? Is there an ideal location for it, or would we need to start a large amount of construction? And it turned out we were very lucky. There is an ideal location that already exists in the LHC infrastructure. So here is a Google Maps picture of the interaction point close to Atlas. So here's Atlas, here's the LHC ring, here's the SPS ring, so the pre-accelerator. And there is this additional tunnel, TI-12, which connects them. This used to be the injector during the lab era, but it's currently unused. They built a newer, bigger, better connector between the SPS and the LHC tunnel. In red, I show the beam collision axis, so the axis of the incoming protons at the Atlas interaction point, so a tangent line along the LHC ring. And you can see it goes through this side tunnel TI-12 at this location. Here I show a picture of how it looks down there from only a couple of years ago. So you see the LHC beam line here, and you see the beam collision axis would go through here, through this tunnel, going through the existing tunnel structures. So we would like to put the FASER experiment in this location, right along the beam collision axis. A lot has happened since then. So this is how the tunnel looked about a year ago. So you still see old ventilation, and you can also see that the tunnel has an incline that goes upwards. Earlier this year, this tunnel has been modified to accommodate the FASER experiment. The trench has been digged that allows to center the experiment right along the beam collision axis, and infrastructure has been introduced, for example, power and lighting and so on. In a couple months, it will look more like in this picture here from our technical proposal, where the FASER experiment is placed right along the beam line, or beam collision axis, and looks like a telescope towards the Atlas interaction point through 100 meters of rock, and looks for particles that move through the rock and decay or interact. So the location has been prepared additionally to preparing the side tunnel for the experiment. Also, there has been additional preparations. For example, stairs have been implemented to allow access to the Phasor location, or a protection has been built above the LHC line so that detector elements could be moved over the LHC. Here I show the structure of the Phasor detector. It consists of a decay volume where we would expect to see the decay of long-lived particles, followed by a spectrometer that again consists of magnets. So the red elements are magnets that are hollow inside, producing a constant magnetic field with a strength of roughly 0.6 Tesla. And in between there are tracking stations, modules, SCT tracking modules that were given to us by the Atlas experiment. It's followed by a calorimeter that would be able to measure the energy of the long-lived particle decay products, which was donated by the LHCb experiment, as well as several layers of scintillators, for example, for triggering and timing, as well as a veto station in front so that we have control over what enters our detector, which allows us to, for example, reject backgrounds associated with incoming particles. You can find our letter of intent and the technical proposal with more details about the detector design in those links here. We also more recently added a dedicated neutrino emulsion detector that's placed in front of Phasor, which is about 1 meter long and has a mass of roughly 1 ton, and will be able to see neutrino interactions. The one question that, of course, immediately arises is what is the how does the environment look like? Are there potential backgrounds for both new physics searches or for neutrino searches? And this has been studied in detail. The long-lived particle as well as neutrinos have TV energies and come from the Atlas IP. So this is the signal we are looking for. And it's shielded from the Atlas interaction point by 100 meters of rock, as well as the LHC infrastructure, in particular magnets and absorbers. So all charged particles will be deflected, or neutral particles like photons or neutrons will be absorbed in the rock. So the only particles that could come from Atlas towards Phasor and transport TV energies are muons and neutrinos. And this has been the flux of these particles have been simulated, and it turned out that Phasor is a remarkable quiet spot. So this is shown in this figure here, where we show the muon flux that goes through Phasor. And you can see that, so here is the outline of the tunnel where Phasor is located, and the white circle is where Phasor will be. And you can see that it's in a remarkable quiet spot, whereas left and right of it, if you go 0.5 meter left or right, you would have a significantly increased amount of muons. And this is kind of the shadow of the magnet. The last magnet that particles that would go through Phasor move through is one of the bending dipole magnets that makes the LHC beam go on roughly a circle. And all the negative muons go in one direction, all the positive muons would go in the other direction. And in between, there is a low radiation environment that's ideal for an experiment to be placed there. There are also, in principle, high energy particles from beam gas collisions or photon collisions with a beam pipe near Phasor But again, we're living in a remarkable quiet spot. So at a location about 500 meters away from the Atlas interaction point, the production of these particles has a local minimum. So if we would have want to build it 50 meters before, we would have 3 or 4 orders of magnitude larger rate of radiation levels. But again, the LHC infrastructure works in our favor. Okay, there are possible backgrounds, for example, particles produced in radiative processes of muons. So for example, a muon could brim off a photon that converts in the detector. That would be a potential background, but these backgrounds can be controlled if we can control the incoming muon flux, and so we can use a scintillator veto station to make sure that these backgrounds are under control. There have also been in situ measurements, for example, a Batman radiation monitor, as well as an emulsion detector that has been placed in these side tunnels. All these measurements are consistent with the simulation I've shown before. Quick summary of our timeline. The experiment was proposed in summer 2017, and quickly after, a FASER collaboration has been formed, submitted a letter of intent and a technical proposal. The physics potential for long particles has been studied. At the end of 2018, we received funding, and at the beginning of 2019, we got approval by CERN. Construction for FASER has started, and we are close to the commissioning stage where the detector will be built in the side tunnel and then commissioned. Soon after, we have proposed the Neutrino Detector and written a technical proposal for it, which was submitted earlier this year. And we expect to take data whenever the LHC turns on again, which by now is probably the year 2022. And we are already thinking about possible upgrades during the high luminosity era. Okay, any questions so far before I go to long-lived particle searches?
Excuse me, I have a quick question. About the neutrino background. You're talking about the muon background, but there should.
I will come to that in, I think, a couple of slides. There I will talk about the specific backgrounds one would have to consider for example, long-lived particle decays. And if I don't answer your question by then, please interrupt me again.
Yeah. All right, thank you.
Okay. So let's look at our first physics case, and that is long-lived particle searches. And again, I linked a couple of papers here, and I will send you the slides after this talk. So these are links, you can click on it. Those are very motivated, and the best motivation is, of course, dark matter. So here is a cartoon how at least I think about dark matter. So we have a standard model sector, and we have dark matter, which might be part of a dark sector. And they need to be coupled somehow. If we go or assume that dark matter is produced in thermal freeze-outs, then the abundance of dark matter would go roughly like the mass scale of dark matter and the possible mediator squared divided by the coupling between the dark and visible sector to the force. And it turns out if we would plug in weak scale masses and weak scale couplings, we can predict the dark matter relative abundance, which has been called the WIMP miracle and motivated a lot of searches for weakly interactive massive particles. However, those searches turned out to be not that successful so far. So the focus has shifted towards a broader range of masses and couplings. And if you look at this formula again, you could see that lighter masses would be possible to give the right dark matter density if we would also have a very light coupling, which means that we would need new mediators between the standard model sector and the dark sector, for example, a dark photon or dark scalar or stellar neutrino or something like this. So this motivates the existence of additional light weakly interacting particle states. Additional motivations come from anomalous experimental results like G-2 or beryllium 8, or more recently the Koto anomaly, and probably many others that I forgot to mention here. And prominent examples, as I already mentioned, are, for example, the renormalizable portals like the dark photon or the dark Higgs boson, but also stellar neutrinos or axions, for example, and many more. Let's look at one very specific example, and that's the dark photon, which probably many of you heard about it. For those who haven't, here's a quick summary. So a dark photon is like the standard model photon, but it's massive. So it has a mass, which I call Ma prime. It couples to standard model particles the same way a photon would, but suppressed by a factor epsilon. So the Lagrangian contains a mass term and a coupling term. It can be produced, for example, or it can be in general produced in any way that photons can be produced. For example, in the decays of mesons. For example, pion could decay into a dark photon, the photon. There are other production mechanisms as well, but this is the leading one for most parts of our discussion. And the dark photon could then, since it's massive, decay as well in charged particles, since it's only couples to charged particles, for example, an electron pair. But the decay rate is very small. That means the lifetime is very large, so we have a long-lived particle that could travel, well, however small you make the coupling, the longer it can travel. So here I show what we would expect to see it in the forward direction. So I mentioned before that dark photons can be produced in the decay of pions. And pions, if you look at all the pions produced at the LHC, we would expect the typical transverse momentum to be of order the pion mass, or lambda QCD. We have validated that using dedicated simulation, and the result is shown here. So here I show the angle with respect to the beam axis, and here I show the momentum of pions. And you can see that they indeed cluster around transverse momentum order of lambda QCD. And these are very dedicated hadronic interaction models that were grounded on various LHC measurements and other measurements. Then the pion decays into a dark photon. Here I show one specific benchmark scenario that's not excluded yet, the 100 MeV dark photon and the kinetic mixing of 10 to the minus 5. And of course, the rate decreases by a sizable amount, in this case, a factor 10 to the minus 10. But you still see, since we had so many pions in the first place, we still produce a lot of dark photons. So indeed, the LHC could be a dark photon factory without us noticing it, which I find pretty remarkable. Again, the transverse momentum peaks around lambda QCD, and note that you will get a sizable amount of dark photons produced at very high energy at very low angle. So it's a very forward direction. And then you can ask, okay, what's the probability of this dark photon to decay within the phasor distance? So within 480 meters plus minus a couple of meters. And of course, it needs to be very energetic to be able to travel that far. If it's very low energetic, then it will just decay before it reaches the experiment. So this is shown in this plot. So these are all the dark photons that can travel far enough, and they're all at a very small angle, which motivates to have a small experiment that can still collect the majority of those decays. So what we're looking for is a production of long particles that can travel 500 meters and then decay into charged tracks, and the signal is very striking. It's opposite sign charged particles with very high energy that originate from a common vertex in a small empty decay volume and point back to the interaction points for 100 meters of rock. There are, of course, backgrounds that could in principle look the same. So for example, well, cosmic rays are not a problem. They would come from above, so that would, of course, look very different than something that comes from Atlas. Neutrino interactions could, in principle, happen, but neutrino interactions would look very different. They produce typically tens of particles and not an electron pair. So those are also not a problem. However, as mentioned before, there could be radiated events associated with high energy muons. So a muon comes in and it ramps off a photon that then converts and produces an electron pair. And this would be by far the leading background if the muon would not be vetoed. However, you can identify a muon relatively easily if you put some scintillators in front and identify all the events that were associated with the muon by just tagging the muon. And therefore, also you're able to reduce those backgrounds to a negligible level. Okay. So we have studied what this experiment then could do for our example of dark photons, and the result is shown here. So this is the Phasor experiments that I've shown before and the reach for various different luminosities. The gray areas are the existing constraints. So you have some prompt searches from, for example, Bell and Barbar, where you just look at the resonant production of dark photon. And then you have long-lived particle searches from older beam damp experiments down here, and the reach of Phasor in yellow. And you can see that only with one inverse femtobarn, so this is a couple of days of running, one would be able to probe currently unprobed regions of parameter space. And with 10 inverse femtobarn, which is maybe a week or two of running, you can already probe a rather sizable region of parameter space. 1/3 of the LHC is roughly 150 inverse femtobarn, and 3000 inverse femtobarn is a high luminosity LHC luminosity, and you can curve more and more in this unprobed region of parameter space. We have also considered a futuristic design called Phasor 2, in which the decay volume would be bigger, and which could be implemented during the high luminosity LHC era, and it would lead to even larger discovery prospects. We have not only studied dark photons, but also looked at a variety of other models. For example, during the physics beyond collider studies that CERN did a couple of years ago. So this includes, for example, dark scalars or stellar neutrinos or various models of axon-like particles. And we have found that Phasor can probe only a few of them, and Phasor 2 can really probe all of them, opening a large discovery prospects that are otherwise not used. So here's a link to our physics case project. Of course, those models are just a small subset of possible models. It's some simplified models, but of course there is a much larger variety of things one can look at. Here I show a screenshot from our Phasor website, which you can reach via this link, where different authors considered different models that could be probed with Phasor, including authors from KIAS with a recent paper on stellar neutrinos with light gauge interactions. Okay, any questions about long-lived particles?
I have another question.
Yeah.
So you've mentioned about the production that coming from the meson decay. Basically, it's coming from the meson decay.
Yeah.
But can it be possible that the right particle itself is produced at the proton-proton collision and travel toward Phasor oscillating?
Yeah, it's a little bit of a question on how you want to describe it. Mm-hmm. So if you if the particle would be heavy, let's say a couple of GeV, you could just say, well, you produce it, for example, quark anti-quark goes to a dark photon. You can do that. But you can't really do that for a particle that has a couple hundred MeV. The problem is not that this process might not happen. The problem is that perturbative QCD is just not the right way of describing things. You can't use perturbative QCD at momentum transfer or scales that are below the confinement scale. So yes and no. That's why going to the hadronic picture is a much better description at low energies. For example, besides the meson decays, which of course are a very great production mechanism, since you can use the hadronic the QCD production cross sections and combine them with the rare decays into dark photons and really get an increased production cross section, which you wouldn't really get the same way for example, for Rayleigh production. But also you just couldn't really describe these low momentum transfer processes just with quark fusion.
Isn't it the same as the IR photon emission, like ISR or FSR?
I talked earlier about proton Bremsstrahlung, and this is nothing else than initial state radiation, right? I said earlier that the dark photon could be produced in any model that produces a photon. So protons can Brem off photons, they do that all the time. And so they can do the same thing with dark photons. And this is nothing else than initial state radiation, just for like a, in the hadronic pictures instead of the partonic pictures. If you would Brem off a photon or dark photon with a larger transverse momentum and your scale gets larger, at some point you wouldn't Brem it off coherently on the proton anymore, but off the quarks, and that's maybe our more familiar initial state radiation picture. So just a question on, at the end, maybe form factors or what picture to look at.
I see. But I guess the photon emission, basically photon emission at the PP collision has been studied, right?
Photon emission?
Yeah, for instance, for the dark photon, it's just simple replacement of the photon by a dark photon. So at the proton-proton collision, the low energy photons can be emitted, right? And such a production rate might be calculated.
Oh, it's certainly been calculated. I'm not sure how much has been measured there. I don't think that has been the focus of many of our measurements, but
for this kind of experiment, the invisible particle, if the invisible particle will be produced at the PP collision, then it can penetrate everything until it hits the phasor, right?
Yeah.
So, but anyway, such kind of contribution has not been included in this picture, right? Is that correct?
It has been. So we have included the Bremsstrahlung contribution, which allows us to go to larger energies or to larger masses, and also produces these interesting wiggles here. So for example, this is resonant mixing of the dark photon with the omega or rho meson, which would lead to an enhanced production at this point.
I see. All right, thank you.
Okay, let's go on to the next topic and the newest topic, and that's neutrino measurements. So neutrinos have been detected by a variety of sources: the sun, supernova, reactors, accelerators, but not from collider experiments like the LHC. We have actually never seen an LHC neutrino. And that's not because we haven't produced them. We produce tons of neutrinos at the LHC. Atlas actually provides some very intense, highly collimated neutrino beam directed at phasors. So we would expect during run through of the LHC all of 10 to the 12 neutrinos to go through the Phasor experiment in a very highly collimated beam with energies of order of a TeV. And we first thought about it as a background for possible background for long-wave particle searches. It turned out to not be a background there. And then we started to think about it as a signal. Could we see those neutrinos? Could we probe physics with it? So we proposed to put a dedicated neutrino detector in front of Phasor, which we called Phasor New. This is a 25 centimeter by 25 centimeter times 1.3 meter emulsion detector with a tungsten target and a mass of 1.2 tons. And doing run 3 of the LHC, so within the next couple of years, we expect to see 20,000 muon neutrino interaction, 2,000 electron neutrino interaction, and 20 tau neutrino interactions. And for comparison, this is more than tau neutrino interactions we have identified worldwide so far. In particular, this is interesting because this is the highest human-made neutrino beam that could possibly be created on this planet. There's no more energetic collider than the LHC, so there's no other experiments that could possibly probe neutrinos with TV energies. And just to give you one idea, and I will talk about more later, one could probe the neutrino cross-sections at TV energies for all flavors where they're currently unconstrained. So here I show the cross-section divided by energy, which is roughly constant, for electron, muon, tau neutrino as a function of energy. And the gray arrow bars show existing measurements, and you have a variety of beam dump experiments that probe neutrino cross-section up to a couple hundred GeV, for example, the highest energy measurements done with the teratron beam. And you even have very high energetic measurements from IceCube, where they looked at, for example, do neutrinos get absorbed in the Earth if the cross-section is high enough, and is therefore the flux of upgoing and downgoing neutrinos different, and they were able to put the constraints there. But there are actually no constraints in the TV region. This has never been measured. And the LHC provides the neutrino beam for free to do this measurement. And so here I show the expected spectrum of neutrinos that would interact in Phasor, and also translate this into a projected sensitivity to measure the neutrino cross-section. And you can see we can fill this energy gap at the TV range where no one else is sensitive. Okay, how would such a detector work? It's an emulsion detector. It's a technology that has been used already for a variety of experiments like Chorus or Donut or Opera. So it consists of emulsion films that are interleaved with tungsten plates. And here's a picture of an emulsion film and a cross-sectional view. So each film consists of 2 emulsion layers made of silver bromide crystals. And if a charged particle goes through this layer of scintillators, it activates those crystals. And after you develop the film, the activated crystals change the color, and instead of being white, they look black. And then this is a picture of a developed film, and you can see those dots here. So apparently a particle went through and left a track in the emulsion film, so you know that there's a track. And this has an amazing spatial resolution. So essentially, emulsion detectors are 3D tracking devices with 50 nanometer spatial resolution, much better than any of the electronic detectors we have. Unfortunately, it's essentially a picture with a long exposure time. It's not a video, so it doesn't have any time resolution on its own. The Phasor New detector would consist of 1,000 emulsion films interleaved with tungsten plates, and would be sensitive to neutrino interactions. Neutrino comes in, and a bunch of charged particles from the interaction come out, which can be tracked through the emulsion detector. And as I will show in the next slide, it will also allow to identify what particles were produced. So here is a picture from the Opera experiment. It's actually a tau neutrino interaction. So the vertical lines are the emulsion layers, and then a neutrino came in, interacted here, produced a neutral vertex. So nothing came in, something comes out. And these colored lines are charged particles that were produced. You can see that there is one particle that does something interesting. It moves a bit, and then it seems to change direction and moves a different direction. And this is exactly what we would expect to see from a tau neutrino that produces a tau, which is short-lived. So this is one of the tau neutrino candidates. You can also see those showers here, which we would expect to see from a photon, so we can identify photons as well. And you can also see this yellow track here, which also seems to change direction. And this would be a low energy particle, which just scatters around via multiple Coulomb scattering. So we could use this amount of scattering to estimate the energies of particles. So Emulsion Detector even provide energy estimates. So detector performance of such a detector has been studied in detail in our letter of intent, and we have found that it allows for flavor identification. We have a rather good efficiency of finding vertices. We can even achieve just with the Emulsion Detector an order of 30% energy resolution. But it doesn't stop there. We would like to connect the Phasor Neutrino Detector with the Phasor detector. So we essentially have a spectrometer right behind it, so it would be stupid to not use it. So we want to interface it with an interface tracking layer. So essentially put another tracking layer right after the neutrino detector, and then match the tracks of, for example, a muon that's produced in the Emulsion Detector with what we see in the interface, and then track it through the rest of the detectors. This would allow, for example, to distinguish muons and antimuons since they bend in opposite direction, and hence between neutrino and antineutrino interactions. It will also allow it to improve the energy reconstruction, and the fact that we can tag the event and timestamp the event allows us to see if anything came in the same event, and therefore veto all sorts of backgrounds that would be associated at the same time with this event. We actually already have data. So I've showed you earlier that we took some data to validate the muon flux from the simulation, and this detector was actually a neutrino detector, an Emulsion detector put down there with a mass of 30 kilograms, the picture shown here. It was exposed for 12 inverse femtobarn in 2018. And the goal is to use this data and analyze it. And this is an ongoing analysis. Possibly see the first neutrino at the LHC and show that, that this approach is feasible and works. We're currently doing this, and here are already some results. So for example, here is the amount of tracks we expect to see in a 2x2 by 10 film area. So you see there are just lots of particles that went through. And we would like to look for a signature where nothing came in and a bunch of track comes out. So it's literally looking for the needle in the haystack. And this is possible. So here is one reconstructed neutral vortex candidate that we found in this amount of data. And this could be a neutrino observed at the LHC. Okay, there are plenty of physics applications that one can do with neutrinos at the LHC. Many of them have not been investigated yet, and I will essentially present all the ideas we had and hopefully stimulate a discussion afterwards, but also maybe even future work based on it. So before I go into there, let me ask again if there are any questions.
Sorry, I have a naive question.
Yeah.
Would you remind me the structure of the phasor? So the neutrino detector comes first, and at the second e-call at the another end.
Yeah. So the neutrino detector comes first, and the e-calls at the end. Yes.
I see. So the can it be possible that any dark particle has been produced at the neutrino detector, and then that gives more event on the e-call behind it?
So you're asking if the neutrino detector could be a source of backgrounds.
Yeah.
Yes, of course, you could produce a particle there. For example, you could have a neutrino interactions in here, and you produce, let's say, a kaon. And the kaon goes in here and decays or interacts with the ecal. That is possible. However, the rate of those events is not higher due to phasor nu. If you wouldn't have the neutrino detector here, you would have rock in front, and the same thing would happen in rock. And roughly speaking, the amount of particles produced in a certain mass is the same as the amount of particles that were absorbed. So phasor nu is shielding us from everything that's produced in the rock, but more stuff can be produced in phasor nu, and those effects cancel each other out.
I see.
And if you're worried about, for example, neutrino interactions producing kaons, this is of course possible. But typically they produce more than just, let's say, one kaon. They typically produce a bunch of particles that you could then veto in this veto station here.
I see.
And if we would have any activity, for example, if you have a neutrino that comes in, typically it has like a couple of 100 GeV or TeV energy. It would produce a big hadronic shower that typically is not fully contained in the detector, so it would certainly go into the first scintillator station here, and then we would know that there were particles produced.
I see. All right. Yep. Thank you.
Okay.
I have a question.
Yes.
In this below figures, the error bar is very getting smaller, around 10, around 1 TeV. That's because the typical energy produced neutrino is 1 TeV.
Okay. Yes. On the one hand, in the center, that's where the statistical uncertainty is smallest because the event rate is the highest. But another effect comes in here. These are mainly systematic uncertainties. So we don't exactly know what the neutrino flux is, because to know the neutrino flux, you need to know the flux of pions, for example, that then decay into neutrinos. But we don't exactly know that. We know that, well, within like a 20–30% uncertainty. We're currently putting quite some effort into better understanding how to quantify these uncertainties, and then also how to minimize them. For example, using different data from other experiments and other measurements to improve our modeling of, for example, forward pion production. What we did here is we compared 3 common models for forward particle production. These are cosmic ray Monte Carlos, typically used for cosmic ray experiments, called EPOS, Sybil, and QGS-JET, and then just compared the 3. And it turns out that they make very similar prediction around 1 TeV, but more different predictions at lower and higher energy. So it's in some sense a more artificial effect of the way how we calculated our systematic uncertainty.
Thank you.
Yeah. This is actually a very interesting topic and one where certainly more work is needed. So if anyone is interested in looking more at this, please let me know. Okay, so let's discuss the physics potential of those neutrino experiments. And the physics potential is related to all parts of the neutrinos at the LHC, their production, their propagation, and the interactions. So let's first look at the physics potential for neutrino physics. And one thing I've, of course, already mentioned is measuring the neutrino cross-section at TeV energies in this unexplored range for all the 3 flavors. And one can do that for charge current interactions, which you have already done, but one could also do that, for example, for neutral current interactions, which we have not looked at. And neutral current interactions are very sensitive to, for example, non-standard neutrino interactions, so neutrino NSIs. And it would be an interesting question to understand if phasor measurements could actually help to further constrain them. Just as a note, all the text that is written in these lighter, more transparent colors are things that we have not looked at yet. So use them as inspiration for future work if you would like to. There are many prospects for tau neutrino physics. So far worldwide, order of 20 tau neutrino interactions have been identified, mainly at Opera and Donut. And we would expect a similar number of tau neutrino interactions at Phasor Nu. But in principle, much larger number, thousands of tau neutrino interactions could be possible during the high luminosity LHC era. One can put the experiment in there for longer, and in principle also make it bigger by an order 1 number, which is not at all unrealistic to do, and turn this into a precision tau neutrino experiment. One can, of course, measure the tau neutrino cross-section, but also other interesting properties. For example, maybe the magnetic moment, or look at rare processes. For example, test lepton flavor universality by a process like nu tau C goes to tau B. That's a very interesting process, because if you turn it around, it's the same diagram as B goes to charm tau neutrino. So that's a process that's associated with our favorite flavor anomalies. So maybe neutrino measurements can help to shine light on this kind of physics as well. We are measuring neutrino interactions very precisely. So Phasor Nu is a very high precision detector, which will identify the event shapes, topology, and kinematics of neutrino interactions very accurately. And this can really help to validate and tune neutrino event generators, like, for example, Genie, which then could be used to reduce systematic uncertainties in other experiments that look for high energy neutrinos, for example, IceCube, which I think would be an interesting and valuable thing to do. One can also look at neutrino interactions, and we have already done a rather preliminary study on it. Of course, there are no neutrino oscillations. Of course, there are no neutrino oscillations expected in the standard model. The baseline is just too short, or the energies are too high. However, if you would have a sterile neutrino with a mass of 40 electron volt, you actually would expect oscillations. So this is shown here. The top part shows the muon neutrino goes to muon neutrino probability. The blue line is the expected spectrum we would have in the standard model, and the orange line is what we would expect, including neutrino oscillation. And we see a sizable difference, already for a coupling of 0.1, which is close to the border of being excluded or allowed. So one could actually use Phasor Nu as a short baseline neutrino experiment, and possibly even probe the anomalies that currently exist, for example, in Alice and the mini-moon data. There is a variety of potential for LHC neutrino detector for BSM physics. For example, tau neutrinos. Tau neutrinos are very rarely produced in the standard model. It's order of factors 1,000 less than muon neutrinos, since they are mainly coming from charm decay and the charm production rate is suppressed. However, you could imagine new light weakly coupled physics that likes to couple to tau neutrinos. And one example would be a B-3L tau gauge boson. That's a renormalizable theory that's gauge invariant. So this is a possible scenario. And you could produce such a gauge boson, for example, neutron pion decay. Pi naught goes to this gauge boson plus a photon, and then if it's light, it really likes to couple to tau neutrinos, so you get a large branching fraction to tau neutrinos. And you might ask, okay, does that do tau neutrino measurements allow to constrain such a model? And the answer is, interestingly, yes. It would be much stronger bound than all the existing direct constraints, for example, from rare pion decays into missing energy and so on. Yeah, so one can actually use long-lived particle decays into neutrinos as a possible discovery channel. One can also look at other things. One can use the neutrino detector to look for dark matter. If dark matter is very light, it could be also, for example, produced in the decay of pions. So you have a pion goes to something like a dark photon plus a photon, and then the dark photon decays to dark matter, and this would have TeV energy. So you would have a very collimated, energetic dark matter beam that goes right towards phasor, and could possibly scatter there. So one can use it as a direct detection experiment. So a question one could ask is, could one probe this scattering in phasor nu? One could also use phasor nu as a muon beam dump experiment, where, as I mentioned before, there's a flux of muons that goes through phasor. We expect roughly 10 to the 9 muons going through phasor during LHC run 3. Is there any interesting physics associated with it? For comparison, dedicated muon beam dump experiment like NA64 with a muon beam would only have order of 100 muons more than phasor nu will have. So I think this is something that might be worth investigating. Or one can use other probes of new physics that likes to couple to neutrinos. So many models of new physics predict new particles coupling to neutrinos, like a stellar neutrino, for example. And I think there are many opportunities to try to constrain such models. Here I show one particular plot or diagram which I took from this paper, where a neutrino could possibly upscatter into a stellar neutrino, which might be long-lived, and then decays. And this could be a signal where you see the interaction in phasor nu and the decay in the phasor spectrometer. So this might be something very interesting to look for. And would also allow it to probe a completely different region of parameter space than if this particle is produced directly at the interaction point, because the baseline would be completely different. So very complementary to the other searches that are already being done at phasor. There is, very interestingly, a lot of application for QCD, although you might not think as neutrino physics as a probe of QCD, but it actually is. So forward particle production, as I mentioned, is not so well constrained. And here I just show you one example from another experiment called LHCF. This is a 0-degree calorimeter built 150 meters down from the Atlas interaction point. And they measured the forward neutral pion production. Neutral pions decay to 2 photons, and they would see the 2 photons in some low luminosity runs. And here you see the data they measured compared with a variety of different models. And you can see, for example, that our favorite generator, at least my favorite generator, Pythia, actually predicts a flux that's an order of magnitude too high. This is pretty bad. This is only one of 2 forward measurements that are currently being done. The other one is measurements of forward neutrons. So the measurement of the forward neutrino flux in all 3 flavors for neutrinos and antineutrinos would provide additional, very complementary data that would allow us to further constrain the forward particle production. So for example, neutrinos from light hadron decays, the light hadron production is typically described by non-perturbative models, so-called hadronic interaction models like those here. We could use the data to further validate and improve those models. And on the next slide, I will show you why that is interesting. But also charm production, which leads to charm decays into neutrinos, is a sizable source of especially electron and tau neutrinos, would also be very interesting, because charm production can in principle be described perturbatively. For example, glue goes to a pair of charms, and therefore this process would allow us to constrain PDFs. So the neutrino flux encodes information at the low X gluon PDF, And this I show here just as a little sketch. So this is the landscape for PDFs. So here you have the momentum fraction X and the momentum transfer Q, or the scale Q. And the shaded areas is the region that's currently covered by various measurements at various experiments, in particular the LHC. And those dots is a region of parameter space that would lead to forward neutrino production that could be probed with FASER. And you see that especially this low X region, it's currently completely unconstrained by other experiments. If you look at the typical PDFs, they start to completely diverge at X of 10 to the minus 5 and have like 3, 4, 5 orders of magnitude uncertainty in the region that's interesting for us. So these measurements, even poor measurements, would allow to provide very valuable data to constrain those PDFs. You can also use neutrino scattering to constrain PDFs. So this is interesting, for example, for nuclear PDFs. Our target is tungsten, which is a heavy nuclei, and the PDFs in heavy nuclei are different than in just protons. You have shadowing, anti-shadowing, and the EMC effect, which cause order of 30–40% deviations of the PDF. And one could ask, can we help to constrain those PDFs, possibly with a variety of different targets? So why only have a tungsten target? Maybe it would be interesting to have different runs with different materials like iron or aluminum or something even lighter. But also one could look at charm-associated neutrino interactions. So neutrino plus a strange quark goes to a lepton plus a charm, so that hadronizes into a d-meson. They are short-lived, but still, due to the great spatial precision of an emulsion detector, you can see their displaced decay and identify those events. Roughly expect that 10% of the events, neutrino interaction events, produce a d-meson with them. And one can use that to constrain the strange quark PDF, which is currently rather poorly or maybe even not at all constrained especially in nuclear PDFs. So all those things that I mentioned are written in these more transparent colors. So they have not been investigated yet, but I think they are very interesting, and it certainly is motivated to do those studies. Finally,
may I ask a question? So I was just curious about this forward particle production. It seems there are some generators that are well fit into the data, but some of them are a bit off the data.
Yeah.
But what is the difference between those two categories?
So those, the three ones here that agree very well are cosmic ray Monte Carlos. So they are written by people in the cosmic ray community. And they're, of course, very interested in forward physics because forward particle production is essentially the center of a cosmic ray air shower. So that's the stuff that they measure. So they put way more emphasis on this kind of physics. And these Monte Carlos, are great in describing pion production. Half of them don't even include charm production because charm is too heavy. And of course, weak interactions are not at all implemented in them. For other generators like Pyrsia, Herwig, Sherpa, the situation is different. They are designed to describe Higgs production, but no one really cared about if they can describe forward particle production or not, because that's just not the focus of the LHC. Which doesn't mean that they can't. So for example, if you retune Pyrsia, so change some of its internal parameters that govern, for example, hadronization or just the diffractive cross sections, you can actually make Pyrsia agree rather well with those measurements. So it's partially due to lack of efforts in tuning the generators, but also lack of efforts in improving the modeling in generators like Pyrsia that have been done for the other generators.
Yeah. Thank you.
And then, of course, one would, for all those generators, at least currently, they only provide central prediction. So we can say that, I don't know, EPOS LHC provides this many forward photons, but it doesn't provide any uncertainty. So that's why previously I said that the uncertainty were estimated by comparing the 3 different generators, which is of course not how we would like to define an uncertainty. I'd like to have for each generator to also produce an uncertainty with it. We can't use the scale and PDF uncertainty since it's not perturbative. But in principle, one could do something different and do the same as we do for PDFs. So not only provide one PDF, but a set of PDFs, or here, not only one generator, but a set of different tunes for each generator to allow it to describe an uncertainty of the generator that would actually have an interpretation as like a 95% confidence level or something. So these are efforts that have started, but that should, much more should happen in the future. And that's not only for Phasor, but these problems are more general and also play an important role in LHC physics, for example. Okay, I've already mentioned cosmic rays a couple of times. So this is, or this should be cosmics, not comics. There are a variety of problems associated with cosmic rays that one could learn something from forward neutrino measurements. So for example, the cosmic ray community is currently debating the so-called muon problem. So cosmic ray experiments have reported an excess of number of muons over the expectations. And they compared what they observed with extrapolations of hadronic interaction models tuned to LHC data. And the discrepancy is like 4 sigma or something. Here's a link where this was reported for the first time. New measurements of, for example, the forward muon neutrino flux would allow it to maybe address this problem. From a different angle, also cosmic neutrino experiments are interested in forward particle production. So, for example, IceCube, which looks for extragalactic neutrinos, has a background from prompt neutrino production. So this is shown here. This is a rather old paper from IceCube, but the situation has not really changed since then. So the gray line is what they expect or the best fit for extragalactic or astrophysical neutrinos. And the pink line here is the limit on neutrino production, prompt neutrino production from atmospheric charm production. So we don't understand forward charm production very well, which leads to like orders of magnitude larger uncertainties for IceCube. So if we could understand forward charm production better, for example, by measuring the forward neutrinos at the LHC, we would help to significantly reduce the uncertainties at IceCube and allowing better understanding of the astrophysics that produces those neutrinos. And currently, we don't really have any data on this, and we also don't have any good theory for it either, and these are the words of Francis Hausen. So that's certainly something that should be looked into. Okay, any questions? If not, let me turn to the outlook and summary. So planning for the future, Phasor and Phasor New have both been approved and funded and are currently under construction, and they will take data during the upcoming run of the LHC in the next couple of years, but they also do something else. They pave the way for a high energy forward neutrino physics program and a search program, which, as I showed, open many opportunities for neutrino physics, new physics searches, or even QCD and cosmic ray physics, and significantly extend the LHC's physics program. In the US, I'm not sure how much you're involved in it, but at least here in the US, we are thinking a lot about the SNOMAS community study process, which is a long-term planning process to identify the priorities of the high energy particle physics community. And as part of the study, we are planning to investigate the full physics potential Phasor and Phasor new during the high luminosity LHC era. So in particular, we propose to upgrade the Phasor detector to a Phasor 2 detector with a larger volume and a longer lifetime, or longer running during a larger luminosity, which allows for enhanced sensitivity for long particle searches, and we wrote an LOI that I've linked here. We also proposed an enlarged neutrino detector with roughly 10 times the mass, and such a detector could observe millions of neutrino interactions, including thousands of tau neutrino interactions at TeV energies, and we wrote another letter of interest there to do that, where we also summarized all the physics ideas that I've presented a couple of slides ago. And beyond that, we're also thinking about to create a forward physics facility which could house these as well as other experiments. So currently, we are really limited by the existing tunnel structure, and all these tunnels have never been built to house experiments. They are purely to house the accelerator. But if they would just be built a little bit differently, there would actually be plenty of space to put experiments like Phasor, Phasor new, or other experiments, for example, dark matter interactions, or milli-charged particles, or whatever else you're interested in. So we are discussing to create such a forward physics facility, ideally with an enlarged area around the beam collision axis, but also containing the support to house these experiments in terms of, for example, electricity and access and so on. And we wrote another letter of intent there. And if you're interested, let us know, and there's plenty of opportunities to help us. We will organize a workshop in the upcoming months. And if you're interested in this, please let me know, and feel free to attend and contribute. So yeah, we would like to invite the high energy physics community, which means all of you, to help us and explore this physics potential of this program. And as a reminder, the LHC will for at least the foreseeable future be the only and highest energy particle or hadron collider that we have. So if we don't use these opportunities now, we will not have them for probably half a century until we possibly build the next biggest collider, if that happens. So not using this opportunity or not doing these exercises now will really, we will lose these physics opportunities for a long time. So I think right now is the right time to ask these questions. And we need a better understanding of what the prospects are. Okay. Just to quickly summarize, I've been talking about the Phasor experiment, which is the newest experiment at the LHC. It's, as I've showed, it's quick. We proposed it 3 years ago, and it's already being under construction and partially built. It's small, it's relatively inexpensive, and here I want to thank our sponsors, the Simons Foundation and the Heising Simons Foundation, as well as CERN for all their support and funding. It's being built right now or installed right now in the current long shutdown 2. It will start taking data during run 3 of the LHC, and we are considering upgrades during the high luminosity LHC era. As I said, there's potential to look for long-lived particles at the LHC and to do neutrino measurements at TeV energies. And I hope I also convinced you that there are many unexplored opportunities, and I would like to ask you to help us explore them. For more information, we have a website. You can click here. And yeah, now I'm looking forward to questions, feedback, suggestions. Thank you.
Thank you very much for a nice talk. So, any questions?
Thank you. I have one question. In the first part of your talk about long-lived particle search, you assume long-lived particle decays into a pair of visible particles. What if the long-lived particle decays two visible particles plus invisible? For example, excite dark matter going to dark matter plus E plus E minus, something like that.
Yeah, we have looked at that in an older paper together with Asher Berlin. Pretty much the scenario you just described, like an excited dark matter decays to dark matter plus some visible final states. That is in principle possible, as long as the energy of the final state particles is sufficiently high. So we have just for, to make a statement, we have said, okay, we consider, or we want the visible final state to have an energy above 100 GeV. Practically, it has to be at least like 30, 40, 50 GeV, because otherwise the particles would be too soft and be deflected away by the magnets. So if you would have a 10 GeV particle, it would not be able to go through the entire phasor spectrometer. It would just be bent away. But if it's above a certain energy, let's say 50 GeV, that shouldn't be a problem. And then you can, in principle, see those. The signal we are primarily looking for, like dark photons, would typically have TeV energies. At lower energies, in principle, you would expect that there could maybe be some backgrounds from, let's say, pion decays or something like this, but on the kaon decays. But we think that we have them under control anyway, so this might not be a problem after all. So yeah, even softer final state should be possible as well.
So do you have any right top of this excited dark matter such as phasor?
Yeah, it's I can send you the link later. It's,
okay, good.
It's called something with inelastic dark matter and phasor, and then probably the first thing that shows up on Google.
I see. Please, yeah. Thank you.
So, another question?
Could you explain more detail about the background estimation in phasor or phasor U?
Can you repeat that?
Could you mention about the details on background estimation in phasor or phasor U?
Can I repeat the background estimation?
Yeah. Let me write down my question.
Okay.
Yeah, my microphone.
Yeah, I have problems understanding you acoustically. I think it's just the sound quality. Well, I think so. For phasor, the signal is a particle that. Let me go back to that slide. Yeah, so it's particles that appear inside the decay volume with a very high energy that originate inside the decay volume, but were not vetoed before, so no other activity in front, that point back towards Atlas through the 90 meters of rock. And we thought very carefully about what could be possible backgrounds. And we said that, well, in principle, you could have something like a neutrino interaction either in the air or maybe in a tracking station. But this would typically produce something that does not look like especially not like a dark photon, but also not like most long-lived particles. So typical neutrino interaction has order of 10 charged particles that were produced, so that looks very different than essentially any model of like long-lived particles. And the rates of neutrino interactions in the air or the decay volume here is that it's just negligibly small. And then we have backgrounds associated with muons. So for example, you could have a muon that ramps off a photon that then converts into an electron pair, for example. That of course would look very much like a dark photon, but as long as we can see the muon, that's not an issue. So being able to identify the muons is very important, and we have put, I think in total it will be 5 layers of plastic scintillators in front to allow to identify them. So for example here, there we have a scintillating layer, some lead shield, more scintillating layer. So if a muon comes through, well, we would expect to see it in the first place. But what is if, let's say, the muon already decayed, or the muon is just like slightly missing or something like this, and we would only have a photon coming in. So that's why we would have a lead shield, so the photon would convert, and we would see its conversion products already in here. So either the muon would come in, or even if it's just a random single photon, which is already by itself very unlikely, even that would convert and we could see it. So those backgrounds we are also not worried about. You could in principle have backgrounds where you have a muon interaction with, let's say, Phasor nu or the rock, producing other particles like kaons that are by themselves long-lived and goes through the shielding and the scintillators and decay. But for those particles to have sufficiently high energy to mimic the signal, and to not have anything else associated with them that could be tagged in the veto station, that's incredibly unlikely. So we're also not worried about this. So in summary, we could not think about the backgrounds that could possibly contribute, but of course, once we turn on the detector, we will know more, and we can calibrate all those backgrounds in situ. For example, we can see how many, let's say, things that look like a dark photon do we expect to see if we tag the muon before and then just multiply by the muon detection efficiency, which for each of the 5 stations has been identified to be larger than 99.8%. So we will not be able to have, or there will not be any muon that goes through all the veto stations undetected. Does that answer your question for the long-lived particles? I can't hear you.
I type.
Yes. Thank you.
Okay. Yeah, for the neutrinos, there actually are backgrounds, especially, and I think I have a backup slide on this. Yeah. So if you would only take the Phasor nu detector without interfacing it with the Phasor detector, in principle, there is a background. You could have a neutral hadron, let's say a neutron that comes in, and it would also look like a neutrino, just a neutral vortex. And this neutron could be produced, for example, in nuclear interactions of muons. So muon plus nucleus produces a neutron plus other stuff. The neutron travels a bit, interacts in the Phasor nu detector. And since the Phasor nu detector is essentially a photo, not a video, we couldn't see everything else that comes with this, or at least not match them. So in principle, there would be a background, and this is how it would look in the energy spectrum. So that would already tell you 2 things. That first, it's deeply falling, and for most part of the energy range, it's actually smaller than the signal. And so we have simulated that, but also looked at, could we possibly separate signal and background? And the answer is yes, we can. For example, for muon neutrino interactions, they would actually look very different than neutron interactions or even neutral current interactions, since we would have a muon candidate which we can identify. So it would indeed look very different. And similarly for electrons, for example, we would see an electron-initiated shower, so a shower that starts with 1 charge tracks and that comes directly from the interaction vertex. So that shouldn't, we should not produce any electrons directly in the interaction otherwise. And tau neutrinos we can identify similar to what I showed earlier from Opera with this King signature. That's also really hard to fake. So we expect that the background will not be an issue. And if you combine Phasor with Phasor nu, with the interface, and then you can timestamp the event and reduce all the muon-associated backgrounds by orders of magnitude, and really resolves this problem, or the background problem, by a lot. So even here, we are not worried at all about backgrounds.
Thank you for your.
Okay. Any more questions?
I think there is no more questions. So thank you for giving me a nice talk. And so I